me first say that when I say a hybrid model here, there are a number of ways to use that term. I'm using this to talk about the combination of several different programming models, or maybe I should say programming systems in the same program. They might be mixed in the same source. You might be combinations of components that use different programming systems. So for example, you might have an MPI program that invokes a library that makes use of OpenMP or that makes use of Coarse Fortran. So those would be hybrid models and hybrid systems. The most common one in use in our community is certainly MPI and Threads, whether it's Threads directly through, say, pthreads, or it's Threads through OpenMP. There are some other interesting choices. I mentioned one already. So combining with Coarse Fortran, you could consider combining with UPC. Those also give very interesting hybrid models. I should say, some people say, I really only want one programming model. Well, then you're in the wrong place, because in some sense, MPI is already a hybrid model, because of course it's MPI plus Fortran, or MPI plus C, or MPI plus C++. So you've gone from 1 to 2. Going from 2 to 3 shouldn't be a big deal. Right? The hardest thing is always going from 1 to 2. And I think because of the age distribution of this group, you're probably mostly already doing hybrid or multi-language programming. So how many of you are like Python users? Yeah, that's what I was, yeah. About to say afraid of it. That's actually a good thing. And so you see the benefits of combining the strengths of the different languages, that none of these languages is perfect for everything. Even Python is not perfect. But we need to be able to put them together. And there are things to be aware of. There are gotchas, as I'm sure many of you already know. And finally, the scale of the machines that are coming, particularly the extreme scale machines, really are going to encourage the use of these hybrid models, in part because you're going to want to make good use of the different kinds of resources these machines are going to have. The machines themselves are not going to be simple, uniform machines. They are going to be very complex, and trying to make one programming system do a great job, not just a good job, a great job of handling that complexity will actually make things harder. So the appropriate way to program these is going to be to combine programming systems that are well suited to the different parts, the different levels of complexity. And right now, the model of, I have an internode programming model and an intranode programming model is often quite good. There are lots of things that you can do in the intranode programming, we saw a lot of them this morning, that can be very beneficial. But despite a lot of effort to try to extend that model to the internode programming, that's proven to be too hard to do in a way that is effective. We're just much better at managing that. And so a good separation, good understanding of how the pieces separate really makes it fairly easy to put these things together. And there are a lot of reasons for doing this. I mentioned a couple of them here. One of the things that we're facing for the extreme scale machines is that the amount of memory per flop or per core is likely to continue to decline. That because of power constraints, size constraints, cost constraints, memory is just not scaling in expense the way you would like. And so you're likely to get more compute units per unit memory than we have today. You're also going to have lots of even threads per core for some definition of core. How do you make use of those? Load balance becomes quite a problem. We've been talking about that. Pete talked about that in his talk. There's so many sources of performance irregularities, means that you have to have a strategy for dealing with those. And one component of a solution is to be able to shift work around in a hierarchical way. So you want to be able to shift work around within a node. and take advantage of things that make that fast. And you also may need to be able to shift work around between nodes. And that's going to require a different approach, both algorithmically and from the programming system. And there are also some algorithmic benefits that you get from these models. So just to sort of recap, MPI describes parallelism between processes, so things with separate address spaces. We heard about thread parallelism this morning. And OpenMP and Threads are common models for this. Threads lets you do more, but it's much lower level. Doesn't help you out as much, and can be quite tricky and technically impossible. So there's a wonderful paper about how threads cannot be implemented as a library. How many of you know about this paper? Right. Okay, so all of you should go and find the paper and read it. That will be so I'm going to disappear after this, but that's my assignment for you for tonight. Because there are a lot of very subtle issues. Yes? Hans with Boom. Yeah, there's like an HP technical report, and then I think it appeared in SIGPlan or something. So, yeah, yes, that's the title. So if you just Google the title, you'll find it. And it should scare you. Okay, so that's a good thing. One of the I know that Barbara said this morning, but I'll emphasize it. One of the advantages that OpenMP has is that the compiler knows what's going on, and that, in fact, is quite critical. It's much more important than you might think. So, in programming for multicore. I really need to change this. It says almost all chips are multicore. I have not been able to find a non-multicore chip recently. The clusters are all multicore. They may be multi-chip, multi-core in the nodes. Even multi-chips may share memory. The common models that you have for this are still, one of the most popular ones is use MPI everywhere. And there are some reasons for that. We'll talk about that a little bit. There are a lot of codes that are using MPI plus OpenMP, or maybe one of the other systems like OpenACC, which is one that we have on our big cray down at Illinois. Some people are using MPI plus Threads. Again, I would only do that if I had a really good reason. It's one of those things where you have to explain why you're doing something so painful. And those last two are the sort of hybrid approaches that I'm going to talk about here. One of the first things I want to say is that there's a lot of myths about this. And maybe most of you are lucky enough not to have heard the myths, but let me go through them. So one myth is that it never works. You should just stay away from combining these things. And there are counterexamples. For example, 15 years ago, we did an application that won the Gordon Bell Prize that used threads to help with the assembly of the matrix. That turned out to be a very good place to take advantage of threads. The flip, of course, is that, oh, it's always a good idea, you should always do it. Also false. There are a number of examples. These are again, somewhat old, but it turns out sometimes if you're very, very careful about managing the locality, there's really no benefit from the hybrid model, and you can do everything with MPI. Another myth is that it requires a special MPI so that you have to go hunt for it or you can't have it on your system. This is one of these, another ones with a sort of asterisk. In reality, particularly for sort of loop level OpenMP parallelism, you don't really require anything special. If you're going to do something really fancy, then yes, you do need something a little bit special, and there's some trade-offs there. But in most cases, you can use whatever MPI you find. And then the one which I've already, I think you can tell I've already been addressing, is that there's this view that a hybrid model must be harder to program than a model that only has one programming model because it's got more things. And in some sense, that's a correct statement, as long as what you're trying to do is write a program. But none of you are here because you want to know how to write a program. You're here because you want to know how to make use of parallelism to get enough performance to do your science. And so performance is important to you. And so what you want to know is how to write a program that performs well enough. Well, that may not be easier with a single programming model. It may be much better to have programming models that are optimized for the different parts of the system that allow you to access the performance. So that's a key here, which is often missed. The other thing to remember too, some people will say, well, you can't possibly do this because how am I ever going to manage MPI with 1 million cores? Well, A, people have already done that, and B, you don't need to, because you can have it 1,000 MPI processes each with 1,000 threads, which is what you might get. Or you might even have it as 1,000 MPI processes, each process of which is a 100 process UPC job, each process of which has 100 threads, and so forth. And that hierarchical model is very similar to the way we tend to solve problems elsewhere. So you almost never solve a problem by taking one method and applying it to everything. You'll almost always solve your problems by taking the appropriate theorems, the appropriate approaches, and combining them together. Okay, so those are the myths. I also want to make a note. I also want to plug Barbara's book. And I have, so this is a really good book. I also have to say that since I'm a series editor, I get a teeny little bit of the royalty when you buy the book. So that's the truth in advertising, but it's still a good book. It's important to note that when I went through those myths, because they weren't entirely true and they weren't entirely false. So programming for hybrid systems, it's not trivial. It does require some care, and you have to be aware of the things that are going to influence the performance, the things that are going to influence the choices. But maybe the last part of this is you will undoubtedly run into people who will complain about, well, they'll complain about MPI, they'll complain about OpenMP, they'll complain about them together. The issues that they're complaining about are almost never about the idea of those systems. It's not about MPI, not about OpenMP, not about the combination of them together. It's about practical problems that they've run into in using them or using them together. And those problems are real, but they're not fundamental. And that's the important thing. So in fact, I had the question yesterday about who do you complain to if something doesn't work right. And this is another place where complaining to the vendor that they haven't made the things either work right or work well together is what you have to do. Because these are not unsolvable problems. Okay. MPI itself was designed from the very, very beginning. MPI 1 was designed to be thread safe. Some people don't know that because in MPI 2, we added different levels of thread safety. So in MPI 1, we tried to avoid the idea of a global state. Some message passing systems had the idea of a current message, and then you could ask questions about a current message. You could add things to a current message. The current message is something you can't do in a threaded system because current to whom? Right? So MPI avoided all those things, and again, there's an asterisk, but pretty much it avoided those things. But as implementers started implementing a thread-safe MPI, they discovered something that we've been making a message about through here quite a bit. And again, you heard it this morning. So there's no perfect answer. There's no perfect choice for some of these implementations. You have various trade-offs in the capabilities and performance you get. And in a consumer market, you can decide where you're going to be. But in a high-performance market, you have to deliver high performance. So what we found was that depending on how much thread safety you needed in an MPI implementation, you paid an increasing amount of overhead to ensure that. And so based on the experiences, particularly that IBM had in doing their MPI implementation, MPI 2 defined 4 levels of thread safety. And so the basic one is thread single, which is that there's, as far as the user is concerned, there's only one thread. Whether or not there's other stuff that's running in the runtime systems is not what we're talking about. It's just the user has one thread, period. The next level is thread funneled. So this is the user process can have multiple threads, but there is one thread, and it's always the same thread that makes MPI calls. Why does that, why is that different than MPI thread serialized, which is there's a process and it has multiple threads, but different threads might be making MPI calls. So why are those different? Hint, you heard this morning why. Remember that, yeah, all that ghastly stuff with flush? That's why. If in funneled, you don't have that problem because all the MPI stuff lives in the same thread. It doesn't have to worry about data being touched by a different thread. In thread serialized, it doesn't have to worry about 2 threads touching the data at the same time, but it does have to worry about that memory consistency. And so it may have to do a little bit more to make sure that the data that it's looking at is current. And then finally, there's thread multiple, which is there are a bunch of threads, and at any time, any number of them might be making any possible type collection of MPI calls subject to a few constraints. And one of those constraints is that it's the same constraint that you have in POSIX, which is that any interleaving of the execution of those threads still makes sense. So it means, for example, you can't have multiple threads calling a collective routine on the same communicator at the same time, because there's no way to figure out what that in fact means. But they could all be making MPI ISAND calls, for example. Yeah.
I was curious what the kind of vendor support level, do they do all these or a subset or?
They typically do a subset. So almost everything was thread funneled. The only difference between thread funneled and thread single is that the implementation may be using some system calls, and those systems calls have to be safe in an environment where the user has multiple threads. So for example, you might need a thread-safe malloc if the MPI implementation is doing malloc, because the user might call malloc. Right.
If you're trying to get portability, do you usually not do the serialized or multiple then?
Well, so the right thing to do is to only ask for what you need. And the MPI routine that's provided for this, which I'll show on the next slide, lets you know what you got. Okay. But the typical effort is to implement multiple and or effectively funneled. And the reason that sort of you implement single, but it turns out that everybody's system runtime essentially supports funneled, so you support funneled. And in fact, so here's the way you call it. So MPI 1 had MPI init. In some sense, this is now deprecated. There's MPI init thread, which has the same arguments. So in Fortran, there's no argc and argv, but there's an IAR. And in Fortran, for this, init thread has no argc and argv, but there's an IAR at the end of this. What you do is you ask for a level of thread support, and it tells you what you've got. Now, some MPI implementations will be built as thread multiple, but they will, the routines will have a branch in them, a conditional check, and there'll be a global, effectively there'll be a global variable that's set at the time you call init thread as to whether, in fact, you asked for thread multiple or not. And so if you do init thread and don't ask for thread multiple, then it may skip some of the overhead that it needs to do in order to be correct in the multi-threaded case. In fact, sort of the default way that MPI-CH is delivered is like that. So you get a single library. It can give you thread multiple, but if you don't ask for thread multiple, you don't get it. So, and that's the default build for clusters. There's you can also build it for certain systems, and they don't all do this. But at this point, for example, the Blue Gene MPI supports thread multiple. Okay, but there is definitely an additional cost. Right. So, for example, if you're going to be using, let me go back here. If you're going to be using OpenMP in a way that is like thread funneled, so you're going to be using OpenMP threads, but you've kept all of your MPI calls in the main thread, then you shouldn't be asking for thread multiple. Yeah.
If all of your calls to MPI are outside of OpenMP parallel regions, then it's fine to just use thread single?
Yeah. Well, you really should use thread funneled, technically. But thread single is almost always going to be fine. Right? In fact, I know of no case in which that would cause you any grief. But according to the standard, it would be technically wrong.
Will MPI behind the scenes maybe make any malloc calls while, like, you make it like out when you're not inside the library, it's still behind?
Yeah, so MPI will make the malloc calls. The reason it always works is that at this point, almost nobody's OS uses a non-thread safe malloc by default. All right, so that's why you get away with it. Okay, so another important thing here is what happens when you make a blocking MPI call. So I'm in the thread multiple case. I've created a bunch of threads somehow. I've done an OpenMP parallel region or pthread create, and I do an MPI receive. What does that do? Well, it's actually a very good question, and the answer in other environments was sometimes it depends. So if you did a read call, a system read call, your entire process might come to a grinding halt. So MPI was very careful to specify that, no, that's not what happens. No MPI call will block anything except the thread that makes the call. So you can safely make MPI blocking calls, and it will not affect the other threads. Now, you still have to, the program still has to be well specified. So you can't do things like have two threads wait on the same request. You can't have one thread doing a send on a communicator and another thread freeing the communicator at the same time. Those are all user errors. And they're user errors that the MPI implementation is not going to be looking for. Right? There's no obligation for it to tell you you've been stupid. Right? So what will happen is sometimes your program will explode. And that's about it. Another important thing, and I mentioned this before, is that the collective, if you do collective communication, it has to be unambiguous who's participating in that collective communication. And sometimes this is said that if I have my threads and they're making these MPI calls, then any interleaving of the order of those calls has to make sense. And all possible interleavings have to work. That's the same thing as saying it has to be unambiguous as to what's going on. Okay, so for example, the example I put here is you can't have some threads doing a broadcast on a communicator and other threads doing a reduce on the same communicator. And if you want multiple threads to be doing collective communication at the same time, you need to have them have different communicators. Okay, so what are you required to get? So it would have been nice if we could have said everybody has to provide everything, but that wasn't an option. Some of the vendors refused to do that. So the standard only requires the most basic level of thread safety, so thread single. And at this point, again, most of the implementations are up to the point where they really are supporting thread multiple, although there are some exceptions. So don't assume that you can get thread multiple. Oh, and then also, if you call MPI init, you're supposed to get thread signal. That was the definition. So again, technically, if you do MPI init, you shouldn't use OpenMP. Right? In practice, again, if you do MPI init and only the thread that called MPI init makes MPI calls, you should be fine. Okay, so let's see what else I want to say about this. I think I've covered most of this. Almost everything does, again, support thread multiple, and many uses of thread parallelism will work even at the thread funneled level, or even at the thread single level. So you really don't have to worry about whether you've got a completely thread-safe MPI. However, you do have to watch out for having too many serial regions, too many critical sections, too many places where you are bottlenecked on the resource. Okay. So we can also look at this paired up with the different sorts of OpenMP. So in thread single, that you shouldn't have any OpenMP. Thread funneled, all MPI calls are made by the master thread. So all MPI calls are outside of parallel regions or master regions or guarded by, there's an MPI is thread main. So you can, a thread can call this routine to find out whether it's in fact the thread that's allowed to make MPI calls. Okay, thread serialized sort of looks like this, where you've got an pragma OMP single in here, where you say just one thread can do stuff, so you can put the MPI calls here, and then MPI thread multiple is you can put the MPI calls anywhere. Yeah.
Just to be clear, so when we are doing MPI thread funneled, only one, the main thread can make the MPI calls.
Right.
But if it's a blocking call, other threads are still free to go and
Yes.
deliver. They don't get blocked.
That's correct. Okay. I should actually check and see whether this is still true for OpenMP 4, some of my statements up here. So some things to watch for OpenMP. There's no standard, is there no standard way to manage memory affinity? And still no, okay. So there are workarounds for this. They're really important to do it right. There's the issue of thread affinity. So where does your thread run? So again, it was mentioned this morning, we think that, oh, of course, the only place you would run your threads is on different cores. This is the only thing that could possibly make any sense. But if I'm writing a web server, I probably want all my threads to run in the same place because I'm using them for a completely different purpose. I'm using them for responsiveness, and they're all touching the same data. So they shouldn't be on different cores. And guess who often controls that choice? So setting affinity can be important. And the memory model, as was mentioned, you have to be really careful. I've seen a number of codes, and here's an example of one of the most horrible things that can happen to you. So you've written a shared memory code. You've decided you want to make it a little faster by eliminating these awful locks and whatnot. So what you're going to do is you're going to move your data over someplace, and you're going to have a flag bit, a flag variable someplace, a little logical or bit. And after you've moved the data, you're going to set that flag, right? Has any of you done that? Come on, fess up. Okay. I know that I'm pretty sure that there is code that your advisors are using that does this, and the problem is that the order in which those operations happen, you might look like the flag gets set after you move the data, but the processor doesn't guarantee that. And the other threads may not see things in that order. Okay, so why is this really bad? Well, if you're doing this with your numeric data, what happens is you instead of reading the current time step, you read the last time step. So you don't get anything horrible. You just get an O of delta T error in your code, right? So the accuracy of your solution goes down and you don't know it. Right? It's the worst possible thing that can happen to you. Right? So you have to be really careful with the memory consistency. And I will reiterate what was said this morning is, don't try to be clever around this. Okay. Some things to watch for when you put together the model. Well, one of the reasons for one of the myths that this never works is this first thing, which is that currently there's no interface for deciding between MPI and OpenMP who gets the cores. And one of the things that you can run into is that they both think that they've got all of them. And they might think, or they might even think that, core 2 is one that nobody's going to use, so I'm just going to use that. And so they all use the same core for their services. So those things can cause terrible problems because all of a sudden your assumptions about how work gets distributed and how fast things run are way, way off. And this can get even worse. So for example, on the blue gene here, you can have up to 4 threads per core. And those 4 threads help hide the latency of the operations. You can hide memory references. You can make use of multiple functional units and so forth. That only works if everybody's pretty careful about the number of threads that they're putting on the cores and what they're doing. And if they're oblivious to what else is going on, it's almost guaranteed that something bad is going to happen. So you get that. There's also competition for resources. So choices on how you decompose the loops, how you schedule things, can be guided in many cases effectively by knowing things about how much memory bandwidth you're using, how much you're going to pipeline and so forth. But again, these things are done under the assumption that there isn't anybody else messing with things. And there's been a little bit of discussion here, but nowhere near enough. And until there is a way to solve this problem and the more general problem, because it's not just MPI plus OpenMP, this is going to be a danger point that you have to watch out for. Okay. Having said that, there are lots of places where this works well. And I'll give sort of 4 categories. So compute-bound loops, fine-grained parallelism, load balancing, and memory-bound loops. And so specifically, if you've got loops that involve a lot of operations per load from memory, for example, the matrix assembly that I referred to, then that's a good place to use multiple threads. But I say compute-bound because most processors don't have enough memory bandwidth to keep all the cores happy if what they're doing is memory references. And so what you really want is code where a lot of what you're going to be doing is computing, and you may be pulling in some data, but you're spending a lot of your time computing. Those are good places to make use of multiple threads. The examples we've been showing you for the MPI part are examples of things which are not compute-bound. They're really memory reference-bound. And they're often not good choices for this. But of course, real computational science codes have much more complicated equations, much more complicated systems. The balance is often more appropriate. Fine-grained parallelism is one of the best places because this is where it's not just a matter of expressing the algorithm. This may make an algorithm practical that is not otherwise usable. So for example, if you look at solution of linear systems with distributed memory codes written with MPI, you tend to do for a preconditioner. So you've got your big matrix. The matrix is distributed across the entire system. And it's done a great job of that. But then you have your preconditioner. And it's quite common to make the preconditioner be the diagonal block of, you take the diagonal block of the matrix that's on your process, and then you do something with it. Maybe you do an incomplete factorization of just that block. And so you get a block diagonal preconditioner. And as you add processes, the blocks, with a fixed matrix size, the blocks get smaller and smaller and smaller, and the preconditioner becomes worse and worse and worse. And so why do you do that? Well, it's because it's a real hassle to do an incomplete factorization across nodes in MPI, because the algorithm pretty much wants to do a tiny amount of work and then get some new data. And so you're in the sort of worst case for MPI where you're sending and receiving single numbers. So you can write this, but it's awkward. There's a lot of overhead to it and so forth. In a shared memory environment, it doesn't run as fast as you might think because there's still overhead from the shared memory, but runs, it's practical to do this. And that means that you can have a preconditioner, your algorithm can take advantage of this. So on a multi-core, multi-node system, say you've got 10 cores and 100 nodes, with pure MPI, you would typically have 1,000 little blocks for your preconditioner. With a hybrid model, I could do 100 much bigger, much more effective blocks that would be spread across those 10 cores. Each of those blocks would be spread across those 10 cores. That really does give you more than just a sort of communication time advantage. It gives you an algorithmic advantage. And that's true even if it's memory bound. Also important, and one of the places where you can pick up, potentially pick up a lot of benefit fairly easily is with load balancing. So if you're going to load balance, that means you have to shift work from somebody who has too much to somebody who has not quite enough. In a pure MPI code, that means that unless you take advantage of the MPI-3 shared memory features, that means that you have to package up all of the data and send it to somebody. If you do this in shared memory, do this with threads, all it means is that you have to indicate to another thread to do some data because they can just access the data by loading it. And the process of giving them that information may be as simple as giving them a pointer to it. And so that gives you a fairly lightweight way to change a code to at least balance work within a node. And in many cases, that's close enough. As if you, some applications are already distributing your work across their nodes so that the load imbalance sort of averages out within the cores of the node, and then they're able to get adequate load balance without ever having to shift work between nodes. Even if you have to shift work between nodes, you may have to do it less often, and when you do it, you might do it more effectively because you would shift a bigger piece, because you would be shifting the work on a node basis as opposed to a core basis. Okay. And then memory bound loops. This is loops where you've got, say, read-only data. In a pure MPI model, everybody has a copy of the same data, which means that copies of the data have to be read into memory, occupy cache, occupy memory bandwidth. If instead multiple threads can share that data, particularly if some levels of the cache are shared, that reduces the memory pressure. And for applications that are memory bandwidth bound, this can give you a significant performance improvement. So an example would be if you have a state table in which you look up values, and everybody's got the same table, then being able to access one copy of the data as opposed to, say, 16 copies of the data effectively gives you more cache, more memory bandwidth. Okay. Doesn't, of course, remember the myths, it always works, it never works. So sometimes pure MPI is still better. MPI has a very rigid Locality model. Locality is often what you need for performance. And so if none of those other things apply and you've got this, then the pure MPI model may be exactly what you need. Another reason to consider either a pure MPI model or a sort of a mixed model. So, rather than think I've got 16 cores, so that means either 16 MPI processes or one MPI process and 16 threads. Well, it turns out, because of the way the systems tend to apportion resources, that you might need more than one process to saturate the interconnect bandwidth. And so you might need 2 processes or 4 processes. So maybe instead of having 16 MPI processes, each with 1 thread, you need 4 MPI processes, each with 4 threads. And so that's another thing to be wary of. And in fact, I was just doing some tests this morning, and if I wasn't a little twitchy about some of the way some of the things were being measured, I'd show you the data, but it basically showed that on Vesta, I get much higher message rates with more MPI processes as opposed to the threads, right? But there's a point where if I have enough processes, then I'm sort of good enough. So you can imagine having, say, 8 processes, each with 2 threads. I do have some older data, so you can, this is one of the things that you may have to look at if you're starting to make this decision or you're figuring out what are the run parameters. So we looked at things like this, where you have one process with multiple threads and you have multiple processes sending to each other. So in some sense, these look identical. So each of these processes has a thread. And the only difference between this picture and this picture is that there's one process here. The oval here is the MPI job. And there are 4 processes here. But our measurements showed that we got different numbers. So they really should have been the same. They weren't. So the different bars here are different choices of threads and processes. And so this was MPICH and OpenMPI running on a cluster. Even here, we got some drop-off out here. This is the 8-thread case. This is the Sun MPI, so you can tell this is an old slide because it says Sun and not Oracle. And this was an old IBM machine, and you see quite a bit of variation here. And again, this doesn't say that the implementations are bad. It just says that there's a lot that you have to look at when you are figuring out how to apportion resources, how do you interact with the different threads and the processes. They're not identical, and it impacts the performance. Okay, so in particular, for example, you can see these. This is processes, this is threads. So there was a big drop-off between doing separate processes and separate threads. Okay, and there's all those there. Okay. Locality is critical, and wonderfully enough, somebody was running something, and they came across this very issue. So the placement of the processes in threads is itself important. And so I'm not talking about affinity here in the sense of putting the thread down and making it stay, which you do want. But it's also important, where do you put it? And it's another example of the importance of topology. So we talked a lot about topology with the MPI processes yesterday, and you were okay, great, I've got that, good, it's gone, I don't have to worry about it again because we're going to talk about threads. Sorry. Here's an example. I've got, say, I have a simple mesh, 2x4 process mesh, and it maps, say, my grid. And say the way the system distributes the threads is round robin. So the thread goes here, 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 there, there, there. And if it maps the ranks that way, what will happen is, so this thread is communicating to the next thread in the graph, which communicates to the next one, which communicates to the next one, and so forth. If you were doing the layout, you would say, well, this one's going to communicate to this one, and this one, and this one's going to communicate to that one, and that one, and this one. This has 3 times as much data moving between the chips as is necessary because of the layout. So if you're in a memory-bound situation, like a mesh sweep, this layout will be 1/3 as fast. So it's not like 10%. This would be 1/3 as fast. And this, and this will happen to you. In particular, again, those operating systems that are trying to place the threads properly for the web servers, this is what they want to do. This is how it's going to get laid out. So by default, you may be getting almost the worst case. So the topology is also important when dealing with the thread layouts. And again, if you've got MPI processes with threads, you still have to, well, maybe I shouldn't say you still have to worry about this. But if you find that you're not getting the performance you would expect, this is one of the places to look at it. Okay. So what are your options? One option is the fine-grained model. So this is the program is single-threaded, except when it's actively using multiple threads. This has the advantage that it's pretty easy to do. You take your existing code, you find some space where you want it to be multi-threaded, you throw in the directives, and you're done. And again, I want to emphasize, no premature optimization. Sometimes this is fine. But it has a lot of potential drawbacks. You've got overheads of going in and out of being multiple threaded. You may have locality and affinity issues because, for example, memory may be associated with one core because of the way you got things started, or even better or worse, the memory may be associated with different cores, but always the wrong one. And also, of course, you get the Amdahl law problem that you limited the amount of parallelism that you may be able to get because your serial sections will limit that. The coarse-grained model is you do MPI init in OMP parallel, blah, 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 in the OpenMP block and call MPI finalize. That will give you lots of parallelism. You don't have to worry as much about the overheads of moving in and out. Once you've solved the affinity, locality, and placement, you're done because everything's going to stick. But it means you've got to look at the whole thing, and you've got to be careful about what you're doing. Okay, let me. And as we, okay, so these are pragmatic choices that gives you things that you can do now. For the programming models going forward, this is really quite a challenging problem. And it's challenging, as I mentioned, because if you have a hybrid system, you've got to, you have to negotiate how you use the resources. And that's going to be, it's just going to be difficult, but they're going to have to do it. You need to be able to share data. And it's one of those things that's very easy to say, but it's in fact quite hard to do in a way that is correct. So you have to have consistent memory models. One challenge that some systems have been facing is that you have two models, they both have very well-defined memory models, they're not the same. Then what do you do? You might decide to pick sort of the intersection of the two as the model, force that on the programmer, or you may say, well, we'll have to do stuff that's fast, which means we're going to have to rely a little more on the programmer to make sure that the code is correct. One of the things to remember here is that if my goal was to make these things elegant, I'd be doing something completely different than what we're doing here. We're trying to get performance, right? If you're doing parallel programming, it's because you've given up on elegance. You're here for performance, right? You really have. You'd like to get as much elegance as you can, as much support as you can, but you're here for performance. That's the thing that you have to get. And so that's the very first thing that the programming systems have to deliver to you. The challenges for the implementation, so that is just to define the model. Then you have to have an instantiation of the model, an implementation of the model. And so figuring out how to share the communication infrastructure has been a challenge. Fortunately, what we're seeing is that a lot of the vendors are essentially solving the problem for themselves. So while we haven't come up with a good standard way or a good community way to provide a sort of common layer, the individual vendors faced with the nightmare of trying to maintain a bunch of different programming models are coming closer and closer to having their own consistent proprietary systems that ensure that their users can make use of these systems together. Okay, and then so in conclusion, hybrid models really are quite valuable. They exploit these sort of complementary strengths. The hybrid models have been optimized for certain parts of the system. These systems are complex. They're built up of the different components. The different models are appropriate for different parts of the components. And that's really the way to look at it, and that's the way to program it. It's also the way to think about the algorithms for them. So another mistake is to decide to design your algorithm as if the machine is completely homogeneous, and then complain about the hybrid programming model because it doesn't match your algorithm. Well, I'll flip that around. I'm going to complain about your algorithm because it doesn't match reality. Okay. There is an evolutionary path to hybrid models. So in the short term, simply getting a little better support for resource sharing. And again, here there's no standards, but there typically are some implementation-specific features help the different systems play well with each other, even if it's a matter of committing them to different sets of resources so they don't know that the other one is there, they just know what they're allowed to play with. In the medium term, we're still hoping that there will be better support for interoperating components, and in the long term that there's a generalized model that includes sort of support for this resource negotiation and, in fact, for dynamic resource assignment. So I'm hoping that that's what you all have to look forward to, and I encourage you to consider the hybrid model as you look at both designing your algorithms and getting more performance out of them. Okay, any questions? Yeah?
Of affinity? How do we take care of affinity?
You take care of affinity by finding out what works on your system. So, so for example, if you're using P-threads, there are P-thread calls for affinity. So there is a standard there. For OpenMP, I think probably if it uses. Yeah. Okay. So yeah, but in some case, so if then. For example, if the OpenMP implementation is using P-threads underneath, then you can use you might be able to use the P-thread calls sometimes to do that. And often, particularly for facilities, big supercomputer facilities, they will know what hacks work on their system. Right? I think that's okay. Just ask the local expert. There is no portable answer right now, which is unfortunate, but that's the way it is.